Okay, now let's talk about our new stuff today, conditional probability. With conditional probability, we have some added, possibly recently added information we want to incorporate. The definition of conditional probability, and this is the way it's read, the probability of A given that B has already occurred. There's your new information. The probability of A given that B has already occurred. Well, you might say, well, what does that mean? Well, how's that going to change anything, the fact that some other thing occurred? Well, let's consider this. Consider we roll one dice. Let's try and make this simple, at least to begin with. Our sample space, of course, with one dice is 1, 2, 3, 4, 5, or 6. That's the only possible things you can roll, right? The number of outcomes in that sample space is 6 outcomes, okay? So the probability of getting a 5 is the number of ways of getting a 5 over the sample space. So how many ways can I get a 5? Only one. So the probability of getting a 5, quite simply, is 1 out of 6. I think you already knew that.
Wait a minute.
What if I said I want the probability of 5 given that an odd number has already been rolled? Now, I have some new information. The new information is that an odd number has been rolled. Well, the number of ways I can get a 5 hasn't changed, has it? There's only one way to roll a 5.
Whoa.
But my sample space has changed, hasn't it? The number of possible ways that I can get an odd number has changed. I've reduced that sample space from 6 items to only 3. Haven't I? 1, 3, and 5. So, that changes everything. The odds of getting a 5, given that an odd number has already been rolled, is not 1 out of 6, but rather 1 out of 3, or 1/3. Let me show you the actual formula for conditional probability. Well, normally, the probability of A and B both happening, we'll say the intersection of A and B, would be the ratio of A and B both happening, the intersection, over our complete universe, every possible thing that can happen, okay? But now we know we can limit what happened. With conditional probability, the probability of A intersection B is still going to have the same numerator, okay? That intersection is still going to be in the top, but we know that B happened. So you see,
I want to tell you my secret now.
our sample size is significantly reduced, all the way from the universe, all the way down to just B. I hope you can see that, okay? Consequently, the formula that we'll use for conditional probability, as long as we're positive that B has already happened, is going to be the probability of A intersection B, not over the sample space anymore, but rather over the probability of B occurring. Let me try one. We have 2 dice rolled this time. Now the sample space for 2 dice normally would be 6 for the first dice and 6 for the second dice. I'm going to differentiate them as red and blue. Will be the number of things that occur in the sample space is 36, isn't it? Let's consider what the probability that a 12 has been rolled. Okay, well, I think you already know that. So there's one way to get a 12, and there's 36 in the sample space, but it's 1 out of 36. What's the probability that a 12 has been rolled, given that at least a 10 has been rolled? Well, now we've got a condition, a conditional probability. We're going to use the probability of A intersected with B over the probability of B. A is that a 12 has been rolled. B is that at least a 10 has been rolled. Well, let's think about this. The probability that a 12 has been rolled is 1 out of 36. What is the probability that a 12 has been rolled and at least a 10 has been rolled? Well, that's what it is. That both of them happened at the same time. It's still 1 out of 36. That's not going to change, remember. It's our sample space that's going to change. What is the probability that at least a 10 has been rolled? How many ways can we have at least a 10? I'm thinking there's 6 ways to get at least a 10. 1 way to get a 12, 6 and 6. 2 ways to get an 11, 5 and 6 and 6 and 5. That makes 3. And then 3 more ways to get a 10, 5 and 5, 6 and 4, or 4 and 6. So there's a total of 6 ways. So our probability of getting at least a 10 is 6 out of 36. So using this formula, our probability of getting that a 12 has been rolled, given that at least a 10 has been rolled, let's reduce it, is going to be quite higher, 1 out of 6. Okay, let's do another one. What's the probability that the red die shows a 5, given that a 10 has been rolled by one of the two? I don't know which one. A 10 has been rolled total. Okay, that the red die shows a 5. Well, how many ways, or what's the probability that both happened at the same time? A red die shows a 5, and at the same time, a total of 10 has been rolled. Well, there's only one way for that to happen, isn't there? One way, a 5 and a 5, okay, to get the 10 and to have a 5 showing on the red die. Okay, what is the probability that a 10 has been rolled, period? How many ways is there to get a 10? Well, there's 3 ways to get a 10. 5 and 5, 4 and 6, and 6 and 4. So the probability of getting a 10 is 3 out of 36. So the conditional probability that the red die shows a 5, given that a 10 has been rolled, if we reduce, is going to be 1 out of 3. That's the way we do conditional probability. Let's try another one. We're going to take a survey of state spending, and it reported that 15% of the families bought a new home. 21% of them bought a new car, and 8% bought both a new home and a new car. That smells of intersection, doesn't it? Now, on the surface, this one might look like it's going to give you a headache, but I'm thinking since they gave us the probabilities of everything, all this is going to be a drill in is putting the right thing on top in these probabilities, okay? Let's figure out what the probability that a family purchased a new car given that they purchased a new home. Okay, remember, this is conditional probability. We'll go through it. It's going to be the probability of both things happening at the same time over the probability of B. Okay, let's see. The probability of A intersected with B, in other words, that they bought a new car and a new home, they gave it to us. How many bought both a new car and a new home? Was 8%. 8% bought both a new home and a new car. So there's your numerator, okay? Your denominator is the probability that they bought B, the probability that they bought a new home, and that they gave us 2. 15%. So 8% over 15%. I'll reduce the percents by multiplying by 100, basically.
Next.
And I've got 8/15. Okay? Let's do another one. The whole idea here is to get in your mind the idea of conditional probability and the formula that you use. What's the probability that a family purchased a new car or that they purchased a new home? Well, wait a minute. We've got an or here. We've got an old trick we're going to use with ors. Remember? The probability of A or B, or I say probability of A union B, is equal to the probability of A plus the probability of B minus their intersection probability. And well, we have all those numbers too, don't we? Okay, let's look back at the problem. The probability of A union B is going to be the probability of A. Let's see, that's going to be the probability that they purchased a new car. That's 21%. plus the probability of B, that's that they purchased a new home, that's 15%, minus the intersection, that's that both happened at the same time, that's 8%. Once again, 21% plus 15% minus 8%. Now, we knew that we were going to use that formula because we smelled that or, didn't we? And that comes to 28%. That's the probability that they did one or the other. We're going to use that number to answer this question. What is the probability that a family purchased exactly one? What I mean, either just the house or just the car, given that they purchased at least one of the two. Okay, this is definitely a conditional probability problem. Well, we're going to have to figure out on the numerator the chance that they purchased exactly one. Well, we'll have to add the two, exactly one house and exactly one car. We can figure out those probabilities from the numbers they gave us. The probability that they figured out that they purchased exactly just a house is going to be 15 minus 8. Now, why do I say 15 minus 8? Well, 15% of them bought a new home. 8% of them bought both. So if I subtract 15 minus 8, I'll get the ones that bought a new home but didn't buy both. In other words, they only bought a new home. So I'll add that to 21 minus 8. Now, why 21 minus 8? Well, 21% of them bought a new car. 8% of them bought both. So if I want the ones that only bought a new car, it would be 21 minus 8. And we'll put that over the number we just figured out of the people that bought either a new car or a new home. We just figured that one out in the last problem. We do a little simplification. 15 minus 8, 7, plus 21 minus 8, 13. So 7 plus 13 is 20 over 28.
Oh, yes.
There's a 5 out of 7 chance that they purchased exactly one, given that they purchased at least one of the two. That was a tough one. But remember, the formula for conditional probability is going to be the probability of A, given that B occurred, is going to be the probability of A intersected with B over the probability of B happening alone.
Thank you, sir. May I have another?
Okay, let's see. Let's do this one. It's always useful to be able to come up with some interesting statements based on a perhaps arguably boring table here. Okay? Well, what we have here is a table that summarizes a survey taken of 100 people. The whole thing adds up to 100 regarding canceling spring break. Some people are for it, and some people are against it. As you can see, we've divided it by party as to who's for and who's against it, and some people have no opinion. Okay? Well, big deal. There's your raw data. What is the probability now that a person answered that they were for it? This is no conditional, just that they were for it. Well, out of the 100, I see 12 plus 8 plus 5 were for it. So 12 plus 8 is 20, plus 5 more is 25. So 25 out of the 100 were for it. Were for, imagine that, for canceling spring break.
Next.
So we reduce that, and we have a 1 out of 4 chance. Okay, so the probability is 1 out of 4 that any person, regardless of their party, was for it. What's the probability that a person was for it given that they were Republican? Now, this is a conditional one, okay? So we're going to have to do the intersection of both over the probability of B. Well, the intersection of both is that they were for it and were Republican. If you look at your table there, how many people were for it that were also Republican is 8. So your numerator will be 8. Now, that's going to be over the total number of Republicans. And the total number of Republicans, if you look at your table, is 8 plus 25 plus 5. you add that up quickly, we're going to get 38. Once again, the probability of both happening at the same time is they're for it and they're Republican. Well, there it is right there, 8, over the probability of B, which is the probability that they're Republican, is 8 plus 25 plus 5.
Is that your final answer?
Well, let's reduce it. And there it is, 4/19. Okay, we'll do a couple more. Get you remembering this formula. What's the probability that a person is a Democrat given that they were for it? Okay, well, let's see. Once again, we're going to have to do A intersected with B over the probability of B. So the probability that they are Democrat and that they're for it. How many people are a Democrat and are for it? I hope you see at the table is 12. Okay, so our numerator will be 12. Now, how many people are just, what's the probability of B, in other words, are just for it? Well, let's look in the for column. And we have 12 plus 8 is 20, plus 5 more is 25. So the denominator will be 25. So we get 12 out of 25. That wasn't so bad, as long as you know the formula. Lastly, what is the probability that a person is a libertarian given that they have no opinion? Well, once again, let's use our formula for conditional probability. The probability of both happening at the same time, their intersection. So the person's a libertarian and they have no opinion. Well, that's easy to read from the table. There's 7 people that are libertarian and have no opinion. So that'll be your numerator. The denominator will be how many people have no opinion. That's B, right? Well, how many people have no opinion total? That's 12 plus 5 plus 7. That's going to be 12 plus 5 plus 7 is 17 plus 7, 24. Okay? So we'll have 7 over 24. It wasn't so bad. Okay? Hopefully from that exercise, you'll get the idea of conditional probability and the formula you use.
Oh, this is my very favorite show. I never miss this one.
Okay, totally new stuff. Let's talk about dependent versus independent events. I'll give you a hint. This is going to be related to conditional probability, the difference between these two. Okay?
I demand an explanation.
Okay. Well, consider. Let me give you a situation. If 40 was one of the numbers pulled in yesterday's lottery, okay? Yesterday's.
What I'm pondering?
Do you think the probability is better or worse that it will come up today? Do you know? Well, you know what?
Pay attention, son. This is for your own.
What about tomorrow? Is the probability, even if it came up yesterday and today, is the probability better or worse that it'll come up tomorrow? Well, you need to know that those are completely independent events. They have nothing. It could come up all three or not. They have nothing to do with each other. Okay? In plain English, I would say they have nothing to do with each other. Let me give you a different one, if I would. Okay, if I pull a jack from a deck of 52 cards, okay, I just pulled a jack. I only have 51 cards left. Assuming I don't put that card back, is the probability better or worse that the next card will also be a jack? Well, that really affected it, didn't it?
Wait just a minute.
Those two events are dependent events because they really affect each other. Well,
This is all very sophisticated.
let's come up with a formal definition of independence. If the probability of A, given that B occurred, is simply the probability of A, and also it has to work the other way too. If the probability and also the probability of B, given that A occurred, is simply the probability of B, then you can see they really have no effect on each other. Then we call them independent. Okay? Basically, if the occurrence of B has no effect on the probability of the occurrence of A, and vice versa, then we define A and B as independent. Now, they're either independent or dependent. So if they're not independent, then we say they are dependent. Now, levels of dependence we'll measure another day, but The idea is, as long as they're not independent, they're somewhat dependent.
Allow me to demonstrate.
Let's do one. Rolling dice, two separate dice, is certainly independent events. If I roll a dice, of course there's 6 possible things that can happen, and I roll another dice, there's 6 possible things that can happen. The probability of getting a 5 on that first green dice is 1 out of 6. We know that. We've done that before. The probability of getting a 5 on the second dice is just 1 out of 6. They're completely independent. Now, the probability of A intersected with B is the same as the probability of A times the probability of B. We know that from the multiplication principle. The probability of getting 2 5s is going to be the probability of getting a 5 on the first dice, which is 1/6, times the probability of getting on the second dice, because they're completely independent. And it'll only work if they're independent, won't it?
I know that, dude.
It's going to be 1 out of 36. You already knew that. The chance of getting 2 5s is 1 out of 36.
I don't understand.
But drawing cards, of course, if you don't replace them, are dependent events. Remember pulling our 2 jacks? The probability of pulling both jacks, okay, from a deck of 52 cards
Not.
is not going to be the probability of getting 1 jack times the probability of getting another jack, because we didn't replace it. This time it's going to be the probability of the intersection of A and B, of getting both jacks, is going to equal the probability of getting 1 jack times the probability of getting a second jack, given that you've already drawn a first jack. You can't just, blow off the fact that you've drawn that first jack, because it is related, because the sample space is 1 card smaller now. So the probability of actually drawing 2 jacks is 4 out of 52, right? Times 3 out of 51. The other 3 out of, assuming we picked a card out of our sample space. Considering that we picked a jack first, the number of jacks will be lowered and the number of cards will be lowered. So everything changes. It's not 4 over 52 times 4 over 52, because they are dependent events. I should say they're not independent events. So consequently, they are dependent events.
Warning, warning, warning.
Now, don't be confused between independent events, the ones that their occurrence has no effect on the probability of the occurrence of the other, and something like flipping heads on 2 coins. Now, coins have no effect on each other, okay? Don't be confused between that and what we talked about last time, mutually exclusive events. Those are events that can't occur at the same time. Independent events can occur at the same time, okay? Mutually exclusive events can't occur. For instance, flipping heads and tails on the same coin. That's mutually exclusive. It can't occur at the same time. Okay? But flipping heads on 2 coins, I can do that. It doesn't have an effect on each other, but I can do it.
In this video, we're going to look at conditional probability, and in particular, the multiplication rule for dependent events. In front of us, we got a full deck of cards. There are 52 cards in total. We got 4 suits, clubs, spades, hearts and diamonds, and we've got 12 picture cards. The picture cards are Jack, Queen and King. What I've done is put together a bit of a practical example or explanation of the multiplication rule. We're going to follow it through and then come up with a generalization and a formula that we can use from here on inwards. So here's a Venn diagram. Event A is going to be now drawing a club. So what I've done, in A, I've put all of the clubs. So event A is drawing a club. Event B is drawing a picture card. So event A is a club, so we can see in A, we've got all of the numbers and then the picture cards. in event B. Event B is going to be now choosing a picture card. Outside, this represents everything that's left. Pretend they're all in neat little piles. So if we wanted to put this information on, and I'll write it here, we've got A and B. In the middle, we've got 3. On this side, we've got 10, as there are 13 clubs in total. We realise that from the pack. And over this side, we know we've got 12 picture cards, so we've got 9 in total. 22, there are 52 in the pack. That leaves me 30 on the outside. The question I'm going to ask is as follows. Given that the card we've chosen is a picture card, what is the probability that it will be a club? So I'll repeat the question. Given that the card we have chosen is a picture card, what's the probability that it's a club? We can see quite clearly from this that if it's a picture card, we can only choose from B here. And the clubs that we've got are in the intersection. And we can see that we're going to have a probability of 3 over 12, which we could break down to 1 over 4. So given that it is a picture card, the probability that it's a club is going to be 3 over 12 or 1 over 4 as we're considering picking from B and we are looking only at the intersection. This gives rise to the multiplication rule. The multiplication rule is the probability of A given B is equal to the probability of A intersection B, so A and B, divided by the probability of B. Now, please bear in mind that this can be written the other way round also. So the probability of B given A is equal to the probability of B intersection A divided by the probability of A. Let's just read this. This is saying what is the probability that I get A given B has already happened? And that's exactly what we've done here. So the probability of me getting A, given that it's in B also, is quite clearly 3 over 12. Now, if we went to the numbers only, we can just work this out by using the formula. And with the addition one, this can be manipulated in many ways as well. So the probability that I get A, which is a club, given that it's also a picture, is going to be the probability of A intersection B, which is going to be 3 of the 52 cards, divided by the probability of B, which is going to be 12 of 52 cards. Quite clearly, the 52s cancel, leaving us now with 3 over 12, which of course is 1 over 4. So the way we read this is the probability that A is going to happen, given that B has already happened, is the probability of A intersection B divided by the probability of B. And hopefully that gives you an idea on how it works. So let's look at it in action, and we will do it now on an example. So A and B are 2 events such that the probability of A is 0.6, probability of B is 0.5, and the probability of A intersection B is 0.4. We need to find the probability of A union B, the probability of B given A, the probability of A given B, and the probability of A given not B. So we can use the formula. So just going back, what we can write is the probability of A given B is equal to the probability of A intersection B divided by the probability of B. So let's fill up our Venn diagram, and it will make it quite clear for us what we're looking for. So the intersection from our previous work, 0.4. Probability of B is 0.5, so this must be 0.1. Probability of A is 0.6, this must be 0.2. If that doesn't mean anything to you, please review all of the material before this, as it's dependent upon it, if you excuse the pun. Okay, so what have we got in total? 0.7, so this is going to be now 0.3. We know all probabilities equal 1. The sample space must be equal to 1. So if this is 0.7, the sample space is 1 minus 0.7. So first one, the probability of A union B. We know the union is all of this in here, so that's going to be nice and straightforward. That's just going to give us the 0.7. The probability of B given A. So let's write that out then. The probability of B given A is the probability now of B intersection A divided by the probability of A. So what we've got then is the intersection is going to be 0.4. So what we'll have is 0.4 divided by 0. And now we can see that the probability of A is going to be 0.6. So we can say, simplifying that is going to give us 2/3 or 0.6 recurring. So the probability now of B given A is the probability of B intersection A divided by the probability of A, which is going to give us it's going to give us 2/3. So let's write that there, 2/3 or 0.6 recurring. So that one's B. The probability of A given B. So all we need to do is use this one here. So it's going to be the intersection, which is going to be 0.4, divided by the probability of B, which is going to be 0.5. And what's that going to give us? 4/5, which is going to be 0.8. Okay, and that's logical. We're just looking for this bit in the whole part there. So that one, C, is going to be now 0.8. The probability of A given not B. So if we write this out, what we're going to have then is the probability of A given not B is equal to the probability of A intersection not B divided by now the probability of not B. So the intersection, A intersection not B, is just this 0.2 here, and we've learned that in our previous work. So A intersection not B is just here, which is going to be 0.2, divided by the probability of not B. We can see that the probability of B here is going to be 0.5. So what we end up with then is 0.2 over 0.5, which is going to give us, what's that going to give us? 2/5, which is 0.4. So D is going to be equal to 0.4. In some later videos, we'll go on to look at independent probability and the result of this, the multiplication formula, in terms of independent probability, but we will leave that for another video. So hopefully the take-home message is as follows. If we look at this now, we can say that the probability of A given B has already happened is the probability of A and B divided by the probability of B, which of course can be written in many different forms, as we've just seen. You could have done these without using the formula and just worked them from Venn diagrams. I personally think it's much easier just to work with the formula and plug in the numbers.
Now, I've given you 3 Venn diagrams up the top here where we've got just 2 sets involved. And each one is different. Now, in the first one, we've got 2 overlapping sets. And we could imagine that A and B, say, stand for number of people doing, say, a particular subject like art and biology. So, just looking at this, we've got 2 people, for instance, doing art only. 3 people doing art and biology. 4 people doing just biology. And 5 people doing neither art nor biology. Now, if we're asked a question like this, what's the probability that someone does art given that they do biology, A given B? Then all we need to do is say, right, okay, they do biology. So how many people do biology? Well, we can see from here, these people, 3 and 4, do biology. They're all in the set here for biology. So that's a total of 7 people. 3 and 4 is 7. So that means our denominator here is 7. We've got 7 people doing biology. Now, out of those 7 people, how many do art? And we can see that out of these 7 people, only these 3 people do art as well. Okay? So it's going to be 3 out of 7. Probability that someone does art then, given that they do biology. So given that they do biology, how many do art? 3 out of the people doing biology. What about this one? The probability that someone does biology, given that they do art. So we know they do art, so that's out of 5 people. That'll be our denominator. And out of those 5 people, how many do biology? There's our art. Only 3 people do biology. So it's going to be 3 out of 5. Okay, well here we've got another Venn diagram. This is a special case when we've got 2 sets that are apart from one another. This is often called mutually exclusive events, where 2 events can't happen at the same time. And in this one, we've got 4 people doing art, 2 people doing biology, 1 person doesn't do both the subjects. There's nobody doing both subjects. So, what about this one here? You might like to pause the video and have a go and then come back and just see if you've got the right answers. Okay, well, if you did pause the video and have a go, let's just see if you've got these ones right. Probability that someone does art, given that they do biology. Well, we know they do biology, so that's out of 2 people. But how many people do art of these biology people? Well, it's none of them. So it's none do art out of the 2 people doing biology. And that clearly is 0. And for this one, probability someone does biology, given that they do art. Well, we know they do art, so that's out of 4. But how many out of 4 people doing art do biology? Well, clearly it is none. There's nobody in this set that does biology. So it's none out of 4, in other words, 0. Now in this one, number 3, this is a situation where all the people doing biology do art. We've got here 1 person does art only, 2 people do biology, 3 people don't do anything. We often call B a subset of A. It's within A. And again, you might like to try these 2 examples. Okay, you can pause the video, come back in a moment and see if you've got the right answer. Well, okay, if you had a go, let's see how you got on. Again, we've got probability someone does art, given that they did biology. Well, we know that they did biology, so there's only just 2 people doing biology, so that would be our denominator there, 2. But of these 2 people, how many did art? Well, both these 2 people did art because they're within A, so it's 2 out of 2 equals 1. Okay, it's guaranteed that if somebody's doing biology, they will be doing art. What about this one? Probability of B given A. So we know that they do art. So how many people do art? Well, it's 2 and 1. Okay, a total of 3 people doing art. So that's our denominator here, 3 people. And how many do biology? Just the 2 out of all the people doing art. So it's going to be 2/3. Okay, now we'll come on to number 4. In this one, we've got, say, 3 subjects. A for art, B for biology, and let's say C for chemistry. And I've got all the numbers here of different numbers of people doing various subjects, okay? Just quickly run through some of these. Just to remind you, 1 person here does art only. This 2 here is 2 people do art and biology, but not chemistry. The 5 do all 3. This 3 here, 3 people do biology only, and so on. 8 people. 8 people don't do anything. Well, I've got a few questions here that basically extend just these ideas up here only to a question with 3 sets, art, biology and chemistry in this case. So you might like to pause the video and just have a go at these ones, see how you get on. Well, let's just run through these. First one then, probability that someone does biology given that they do chemistry. So we know that they do chemistry. So how many people do chemistry? That's going to be our denominator. The number of people doing chemistry is in C. That would be to add up the 4, 5, 6 and 7. And if you add up 4, 5, 6 and 7, you should find you get 22. So 22 people doing chemistry. And of those people doing chemistry, what's the probability that someone does biology? Well, it'll be these two categories here, 5 and the 6. 5 people do all three, but they certainly do biology. 6 people do just biology and chemistry, but nonetheless they do biology. So it's a total of 11 people, 5 and 6. 11 people do biology compared to those doing chemistry. Let's look at the next one. Probability of doing all 3 subjects given that someone does 2 subjects. Okay, so how many people do 2 subjects? Well, I haven't said 2 subjects only here, okay? So it's just doing those 2 subjects, given that they do 2 subjects. Now, that would be this 2 here. These 2 people do 2 subjects, art and biology. 4 people here do art and chemistry. 6 people here do biology and chemistry. But you've got to be careful. I didn't say just doing 2 subjects, that they do 2 subjects. Now, these 5 people here do 2 subjects. Okay, they do 3 subjects, I know that, but they do 2 subjects. So, for the denominator here, it's going to be the sum of 2, 5, 4 and 6. And if you add that up, you're going to get 17. 2, 4, 5 and 6 comes to 17. So that's our denominator. And how many of these people in this region in here do all 3 subjects? Well, it's these 5 people. So it's 5 out of 17. And for this last one, what's the probability then that someone does art and biology given that they do not do chemistry? Well, if they do not do chemistry, that's going to be the people outside of C. And that's going to be the 1 person here, these 2 people, these 3 people, and these 8 people. Okay, 1, 2, 3, and 8. They're the number of people that do not do chemistry. So if you add 1, 2, 3, and 8, that comes to 14, and that's your denominator here, 14. So of these people, how many do art and biology? So of these people, that's the 1, 2, 3, and 8, how many do art and biology? Well, it's going to be just these 2 people here. Alright, so that'll be 2 out of 14. Now I know that this cancels down to a half, and I know this cancels down to 1/7, but I'm just leaving them like that just so that you can see how I got my particular probabilities.
You've tested positive for a deadly cancer that afflicts 1 out of 1,000 people based on a test that is 99% accurate. What are the chances that you actually have the cancer? By the end of this video, you'll be able to answer this question. Suppose that in front of you are 2 bowls labeled A and B. Each bowl contains 5 marbles. Bowl A has 1 blue and 4 yellow marbles. Bowl B has 3 blue and 2 yellow marbles. Now choose a bowl at random and draw a marble uniformly at random from it. Based on your existing knowledge of probability, how likely is it that you pick a blue marble? How about a yellow marble? When the number of possible outcomes is finite and all outcomes are equally likely, the probability of an event happening is the number of favorable outcomes divided by the total number of possible outcomes. Out of the 10 marbles you could choose from, 4 are blue, so the probability of choosing a blue marble is 4 out of 10. There are 6 yellow marbles out of 10 total, so the probability of choosing yellow is 6 out of 10. What if you must draw from bowl A? What's the probability of drawing a blue marble given that you draw from bowl A? Let's go back to the table and consider only bowl A. Bowl A contains 5 marbles, of which 1 is blue, so the probability of picking a blue one is 1 in 5. Notice that the probability has changed. In the first scenario, the sample space consists of all 10 marbles, because we are free to draw from both bowls. In the second scenario, we are restricted to bowl A. Our new sample space consists of only the 5 marbles in bowl A. We ignore the marbles in bowl B. Restricting our attention to a specific set of outcomes changes the sample space and can also change the probability of an event. This new probability is what we call a conditional probability. This is standard notation for conditional probability. The vertical bar is read as given. The probability we are looking for precedes the bar, and the condition follows the bar. In the previous example, we calculated the conditional probability of drawing a blue marble, given that we draw from bowl A. Now let's flip things around. Suppose someone picks a marble at random from either bowl A or bowl B and reveals to you that the marble drawn was blue. What is the probability that the blue marble came from bowl A? In other words, what's the conditional probability that the marble was drawn from bowl A, given that it is blue? Going back to the table, because we are dealing with the condition that the marble is blue, the sample space is restricted to the 4 blue marbles. Of these 4 blue marbles, 1 is in bowl A, and each is equally likely to be drawn. Thus, the conditional probability is 1 out of 4. Notice that the probability of picking a blue marble, given that the marble came from bowl A, is not equal to the probability that the marble came from bowl A, given that the marble was blue. Each has a different condition, so be careful not to mix them up. We've seen how tables can help us organize our data and visualize changes in the sample space. Let's look at another tool that is useful for understanding conditional probabilities, a tree diagram. Suppose we have a jar containing 5 marbles. 2 are blue and 3 are yellow. If we draw any one marble at random, the probability of drawing a blue marble is 2/5. Now, without replacing the first marble, draw a second marble from the jar. Given that the first marble is blue, is the probability of drawing a second blue marble still 2/5? No, it isn't. Our sample space has changed. If a blue marble is drawn first, you're left with 4 marbles, 1 blue and 3 yellow. In other words, if a blue marble is selected first, the probability that you draw a blue second is 1/4, and the probability that you draw a yellow second is 3/4. Now, pause the video and determine the probabilities if the yellow marble is selected first instead. If a yellow marble is selected first, you are left with 2 yellow and 2 blue marbles. There is now a 2/4 chance of drawing a blue marble and a 2/4 chance of drawing a yellow marble. What we have drawn here is called a tree diagram. Tree diagrams help us to visualize our sample space and reason out probabilities. The probability assigned to the second branch denotes the conditional probability given that the first happened. We can answer questions like, what is the probability of drawing 2 blue marbles in a row? In other words, what is the probability of drawing a blue marble first and a blue marble second? This event is represented by these 2 branches in the tree diagram. We have a 2/5 chance followed by a 1/4 chance. We multiply these to get 2/20, or 1/10. The probability of drawing 2 blue marbles in a row is 1/10. Now you do it. Use the tree diagram to calculate the probabilities of the other possibilities: blue-yellow, yellow-blue, and yellow-yellow. The probabilities each work out to 3/10. The 4 probabilities add up to a total of 1, as they should. What if we don't care about the first marble? We just want to determine the probability that the second marble is yellow. Because it does not matter whether the first marble is blue or yellow, we consider both the blue-yellow and yellow-yellow paths. Adding the probabilities gives us 3/10 plus 3/10, which works out to 3/5. Here's another interesting question. What is the probability that the first marble drawn is blue, given that the second marble drawn is yellow? Intuitively, this seems tricky. Pause the video and reason through the probability tree with a friend. Because we are conditioning on the event that the second marble drawn is yellow, our sample space is restricted to these two paths. Of these two paths, only the top one meets our criterion, that the blue marble is drawn first. We represent the probability as a fraction of favorable to possible outcomes. Hence, the probability that the first marble drawn is blue, given that the second marble drawn is yellow, is 3/10 divided by 3/10 plus 3/10, which works out to 1/2. I hope you appreciate that tree diagrams and tables make these types of probability problems doable without having to memorize any formulas. Let's return to our opening question. Recall that you've tested positive for a cancer that afflicts 1 out of 1,000 people based on a test that is 99% accurate. More precisely, out of 100 test results, we expect about 99 correct results and only 1 incorrect result. Since the test is highly accurate, you might conclude that the test is unlikely to be wrong and that you most likely have cancer. But wait, let's first use conditional probability to make sense of our seemingly gloomy diagnosis. Let's use a tree diagram to help with our calculations. The first branch of the tree represents the likelihood of cancer in the general population. The probability of having the cancer is 1 in 1,000, or 0.001. The probability of having no cancer is 0.999. Let's extend the tree diagram to illustrate the possible results of the medical test that is 99% accurate. In the cancer population, 99% will test positive correctly, but 1% will test negative incorrectly. These incorrect results are called false negatives. In the cancer-free population, 99% will test negative correctly, but 1% will test positive incorrectly. These incorrect results are called false positives. Given that you test positive, our sample space is now restricted to only the population that tested positive. This is represented by these two paths. The top path shows the probability you have the cancer and test positive. The lower path shows the probability you don't have the cancer and still test positive. Now pause the video and determine the probability that you have the cancer given that you test positive. The probability that you actually do have the cancer given that you test positive is given by the following expression, which works out to about 0.09, less than 10%. The error rate of the test is only 1%, but the chance of a misdiagnosis is more than 90%. Chances are pretty good that you do not actually have the cancer, despite the rather accurate test. Why is this so? The accuracy of the test actually reflects the conditional probability that one tests positive, given that one has cancer. But in practice, what you want to know is the conditional probability that you have cancer, given that you test positive. These probabilities are not the same. Whenever we take medical tests or perform experiments, it is important to understand what events our results are conditioned on and how that might affect the accuracy of our conclusions.